You're watching this video because you want to know certain things about concentrations, don't you? You want to know more about the concentration field, and I'm here to give it to you. So let's crack those knuckles and take out those pens, because we're going to talk about a concentration unit that you probably haven't discussed in a traditional chemistry class. And that's because they don't like to talk about it, because it's not molarity. Right? Let's face it. If it's Chem 151 and 152, they pretend like the greatest, best thing ever is molarity, and that's all that they want to talk about. That's all that they want to discuss. Molarity, 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 molarity. But guess what? Molarity, like I've said before, is not the common unit in a laboratory, people. It's not, especially in an analytical laboratory. Very few times will we actually see solutions being presented in molarity. M-O-L-A-R-I-T-Y. You've already watched those videos, right? It came before this one. Very few times do we work with the big capital M. So I want you to go and burst people's bubbles, especially if you're talking 151 or 152, and if you're taking those courses right now. Tell your instructors, molarity is not the most important unit that's in a lab. And the reason is because it's so strong, right? Molarity is so strong that in an analytical world, it doesn't make sense to report these numbers. We can go so much smaller. We can pick up things that are so less concentrated than molarity that we stay away from molarity for that reason. And because of that, we have different units. So molarity was a very good starting point. And that's why they introduced that in 151 and 152. But there's so many other options that are out there. One of those is called normality. Very similar to molarity, but it's different. And instead of a capital M, it's going to be a capital N for Nancy. So normality has to have a role. Why is this separated? Well, one of the reasons is that normality really plays a role in the field of acids and bases. That's where we see the majority of it. So molarity is used for salts and maybe for some liquids and some solvents and large amounts of them. Molarities are typically whole numbers or fractions of a whole number, like 0.25 molarity, 0.5 molarity, 0.1 molarities. But those are strong based on what our equipment can see in a laboratory. Those are strong for normal solutions and standards that we might make in a laboratory. So an alternative to this is normality. Now, normality is still strong. Don't get me wrong, it's still a strong unit. We're talking about quite a bit. But this has a specific focus on acids and bases. So hydrochloric acid, sulfuric acid, sodium hydroxide, potassium hydroxide, all of these are acids and bases that are used in the lab, and we typically report those in terms of N for normality. The reason is because normality doesn't really play a part with moles. Moles is molarity. There's not a mole word in normality, right? So what normality plays off of is something called the number of equivalence. N, normality, N for number, number of equivalence. Okay. What does that mean? Well, let's take a look. Let's say I go take a jug of hydrochloric acid in the lab, HCl. And let's say I put that HCl in water. It's already in water, right? That's why it's called the acid. That's why it's a liquid. Someone's already done it for me. That hydrochloric acid is dissolved in water, and that hydrochloric acid is breaking apart. And it breaks apart into H plus and Cl minus. And that's swimming around in the solvent, right? And that's the definition of an acid. The definition of an acid is something that gives off a proton. And that is giving off a proton. It's spitting it off. It's a strong acid, right? And the reason that we call it a strong acid is because it gives off every single proton that it has. It hates the protons. Spits them out all over the place. And all of these little protons are swimming around in the pool of water, and they're free, and they can participate in a reaction. Okay. Molarity, the big M. Molarity will come in to play, and molarity will focus on the entire molecule. What is the strength of the entire molecule? Okay? So to calculate molarity, think about what we did in previous videos. We looked at HCl, we got formula weights, we converted the grams to moles, and we divided by liter. Mole per liter. Moles of stuff divided by the liter. So moles of stuff divided by the liter. Normality doesn't do that. Normality means number of equivalent. Well, what does that mean? Well, it really depends on what we're talking about. It depends on the type of compound that we're using. Numbers of equivalent can be anything, right? We're going to find that normality plays a strong role in acids and bases, but we're also going to find that normality also can be associated with salts. So the number of equivalent what? Well, an acid is in terms of proton. How much proton can it release? So when I calculate the normality of an acid, what I'm doing is I'm really only focused on the hydrogen content, because that's what makes it an acid, right? That's it. I don't care about the chlorine. Chlorine doesn't make it an acid. The chlorine's just there hanging out. It's the H plus that makes it an acid. So molarity looks at the entire compound, and it gives me an idea of the concentration of the entire thing. Normality looks at just the proton in regards to an acid, and it gives me an idea of the concentration of the proton only. Not the whole thing, just a piece of it. Just a part. Well, here's the good news. I'm going to show you a quick way to go from normality to molarity, as long as you know the formula. And this is where we're going to start with our normality calculations. So let's say that we have hydrochloric acid, and let's say that this is a 6 molar solution, and we want to calculate the normality of that solution. This is what you need to think to yourself. Oh, normality. Well, this is an acid. How many protons can it give up? Well, this HCl can only give off 1 proton. That's it, 1 hydrogen. So in this case, a 6 molar solution is also a 6 normal solution. Because for every molecule, I get 1 hydrogen. It's 1 to 1, right? Kind of like stoichiometry in a way. It's a 1 to 1 ratio. Every 1 molecule of HCl, I get 1 proton. No big deal. Those are easy. Those are the quickest normality problems. Those are the easiest normality problems, and I never should get those wrong, right? Well, the same thing would happen to a base. So, for instance, if I had NaOH and I had 6 molar solution of NaOH, well, a base is in regards to OH, right? Not every single time, and I guess that we need to describe this as a proton acceptor. How many protons could it accept? But looking at the OH content typically will give us the right answer every single time, as long as it has an OH present. So a 6 molar NaOH solution, well, there's just one group of OH there, right? That's it, just one. For every molecule of NaOH, I get one group of OH only, right? So a 6 molar NaOH is also a 6 normal NaOH. It's as easy as that. 0.2 molar hydrochloric is 0.2 normal hydrochloric. A 0.001 molar sodium hydroxide is a 0.001 normality sodium hydroxide. It's the same number, people. There's no difference between the two. Okay? All right, well, what if it's not a 1-to-1? How do I know? That's pretty simple. Look at the structure. H2SO4. Let's say that we had a 6 molar solution of sulfuric acid, H2SO4. All right, so with this one, for every one molecule of sulfuric acid, I get 2 hydrogens, right? So let's say that this is my little molecule of H2SO4, and there's a hydrogen hanging off and one hydrogen hanging off there. Well, for every one of these, I get 2 protons, right? If normality is in regard to proton, then what needs to happen here is that I take the concentration of the whole thing, 6 molar, and I multiply by 2. So this is a 12 normal H2SO4. That's all there is to it. This means 6 molarity in terms of the compound as a whole, as a group. This means the concentration of the hydrogens that it can spit off. And that's what we call that equivalent. How many protons comes along with one molecule of the stuff? Therefore, every one molecule is equivalent to 2 protons in this case, because that's what it brings to the kitchen table. What about phosphoric acid, H3PO4? Let's say I have a 3 molar H3PO4. Well, if this is my molecule of H3PO4, there's 3 hydrogens that are hanging off of that molecule, right? 1, 2, 3. So for every one molecule that comes on board, it's bringing with it 3 hydrogens. Therefore, one molecule is equivalent to 3 protons. So what I would do is I would take my concentration in molarity and I would multiply it by 3, because every one molecule brings 3 to the table. So 3 times 3 is non-normal. Bases would be the same way. Calcium hydroxide, CaOH2. Let's say that I have a 2 molarity. Well, if I wanted to calculate the normality of hydroxide, I would take the concentration 2 and I would multiply it by how many the molecule brings. So 2 times 2 is going to be 4. So that's 4 normal of OH. Okay? Now, typically the rule of thumb is to write down the entire structure. H3PO4, H2SO4, CaOH2. That way people know what you're using, right? They just don't want you to write down proton, or up here, proton, or down here, hydroxide. Even though that's really what it's referring to, 4 normal of the hydroxide content, 9 normal of the hydrogen content, 12 normal of the hydrogen content. We like to have more background information. We like to know where that's coming from, what molecule is actually present in that container. So we write the entire thing, but we have to understand that that is representative of the proton in terms of an acid, or a proton acceptor / hydroxide in terms of a base. So that's the relationship between molarity and normality. Now, where we get confused is the problem sometimes will say, hey, you've got a 12 normal solution of HCl. What is that in terms of molarity, right? Well, this one's going to be easy because we said it's 1 to 1. We get 1 proton for every 1 molecule. So normal also means molarity. 12 normal is 12 molarity. But what if we had like H2S as the acid and we had 6 normal? What is that molarity-wise? The way that you got to think about this, normality is always bigger. Normality is always a bigger number. The reason is because we're only looking at parts of the molecule, and if it's even, it's even. It's the same number, right? But if those parts bring with it more than 1 hydrogen or more than 1 OH group, then normality is always a bigger number. So in this case, you've got to divide. It's backward, right? So 6 normal H2S, well, 6 divided by 2 is 3. So that's actually a 3 molar solution because we're looking at the entire molecule now. That's what molarity looks at. Normality looks at just the individual pieces. Molarity looks at the entire thing. Okay? So a non-normal H3PO4, what is that molarity-wise? Well, normal's a bigger number. So that means I'm going to have to divide. 9 divided by 3 is 3. So 3 molar would be the concentration of a non-normal phosphoric acid. So that's the very first type of problem that you're going to have to be comfortable with. You're going to have to be able to go from molarity to normality and backward to solve some of these problems. And this is very common in a laboratory when it concerns solutions and standards. You're going to be given solutions that have normal on them instead of molarity. So let me tell you a story about what happened to me as a research assistant with the Department of Anesthesiology. So I was working in a lab at UVA, and in that lab we were working with frog eggs. We would basically cut open the frog, we would take out the eggs, and we would harvest those eggs and keep them contained to do various experiments with them, right? But we weren't torturing. We would sew the frogs back up because they were under anesthesia. So we would sew them back up, and then we would make sure their wounds healed, and they would wake up from the anesthesia. They just had removed the eggs from them, right? So they would go out about their own little business, and they would live happy ever after until we decided to do it again. So at UVA, this is what we would do. Just part of our job as a research assistant. So in that recipe, I was given a laboratory protocol. And in that protocol, or in that lab experiment, they kept saying that I needed a 6 normal H2SO4 solution. And this solution was used in what we would call the egg broth. So there would be a certain point in time where we would take these eggs and we would put them into a solvent, and that solvent had 6 normal H2SO4 present. Well, I was in charge of making this solution and going through a traditional 4-year degree route, taking chemistry 151 and 152. They never really told me what the N stood for. You can kind of see where this is going. So when I started working for the lab, no one really explained it to me. No one really gave me the directions on how to properly make it. Even though it should have been built into the standard operating procedure, it was not. So I just assumed that that 6N was equal to 6 molar. Well, I made 6 molar sulfuric acid, not 6 normal sulfuric acid. And then weeks went by and they kept saying, our frog eggs are dying. We do not know what the problem is. Every time we take these eggs out, we're putting them into this broth and they're basically dying on us quicker than what we expected. There's got to be something wrong with the solutions because we're wasting our time. We're wasting all of our manpower. We're wasting all of our hours, our harvest time. Everything is going wrong, and we don't understand what's happening. We've done it the same way since day one. Well, I kept my mouth shut. I didn't tell anybody about it. And then they figured out that the solution was probably getting made wrong. They didn't necessarily blame me, but I didn't stand up and take the credit for it either, trust me. So what was happening here is that I assumed normality was the same as molarity, and it was not. Of course, now we know that. I'm telling you that now from personal experience. A 6 normal solution was 6 normal in regards to the acid. And now we know that 6 normal is always bigger than molarity. So 6 divided by 2 is 3. I should have been making a 3 molar H2SO4. I should not have been making a 6 molar H2SO4, and that's what I was doing. I was making the acid double the strength than what was required in the laboratory procedure. So don't be a Tracy, especially in the lab. Don't be making this mistake when it concerns normality and molarity. So this is just acids and bases, and I'm going to stop the video here. In the next video, we're actually going to talk about normality in terms of a salt, because we can do that as well. And then we'll go through and talk about other calculations that relate to normality, just like molarity, but we're reporting in instead of M.